So picking up with where we left off on Friday, we were talking about Henry's law and the solubility of gases in a liquid. And we used this expression S of the gas, which is the solubility of the gas in units of molarity, equals Kh, or Henry's law constant, and pressure of the gas. It's the partial pressure of the gas above the liquid, not the total pressure of all gases, just of the specific gas we're worried about. The Henry's law constant is specific to the substance and specific to the temperature. And so we're going to look at an example of how we can use this to figure out what the solubility is of a particular gas. So let's look at an example here, and apologies for the subscripts, it kind of got lost when I converted it for my iPad. But what we want to look at is the solubility of O2 in water at 25 degrees Celsius when the pressure is 2.3 atmospheres. Now we are actually given the Henry's law constants, we're given one kind of set of conditions, and so we can use our formula to find out the solubility. So we're asking for the solubility of O2. It's equal to Kh, and because we're at 25 degrees Celsius, I can use this table because we're also at 25 degrees Celsius, and it tells me that the value is 1.3 times 10 to the minus 3 molar per atmosphere, and then I'm going to multiply that by the partial pressure of 2.3 atmospheres, and when I do that, I get my solubility of oxygen equal to 2.99 times 10 to the minus third molar. So we have very small concentrations of oxygen even at very high pressures. If I want to increase the amount of oxygen that's dissolved in the gas, I'm going to have to increase the pressure or decrease the temperature, because when I do, it's going to change the value of the Henry's law constant. Now, another way we can look at these problems, sometimes we're not always given the Henry's law constant values like we are here. We're actually given two conditions, and we can use the equation once. So we can say if we were given a solubility and a pressure, we could use that information to find the value of Kh, and then use that Kh and say some new pressure to find solubility. And we can do this as long as we're at the same temp and we're talking about the same substance. So we don't always have to be given the Kh value to be able to find something about the solubility or the pressure. Now what we want to worry about are concentration units. We talked about molarity in 105, the moles of solute over the liters of solution, and we need to be careful to notice these definitions. So these are definitions of a lot of different things. Most of this we've seen before. The big new one we haven't seen ever is molality here, and this is different from molarity because it's still the moles of solute, but now on the bottom it is the mass, and it is just the solvent, so not the solution. We have to be careful about that. Mole fraction we looked at a little bit when we talked about some partial pressures, moles of the solute over the total moles, so moles of part A over the moles of A plus B, for example. Mole percent is basically mole fraction times 100. We don't use this one too often, but we do see it occasionally. Parts by mass, so we can talk about percentage, which is really a part, because in percentages we always have a part over a whole times 100, and that's what makes a percent. Well, a part per million or a part per billion are very similar, only instead of multiplying by 100, now we're multiplying by a different amount. So set up exactly the same way, just multiplying by some different factor. So those are all kind of similar. And then we can look at parts by volume, and it's the same thing, only the difference is that we are looking at volumes instead of masses. We tend to see parts by mass more often than we do parts per volume, but occasionally, such in healthcare, sometimes you will see the parts per volume. But the big one we're going to worry about is molality, and talk a little bit about mole fraction, but primarily dealing with molarity and molality, and specifically how we convert from one to the other. Also note that we have a capital M here for molarity and a lowercase, usually italicized M, for molality, so you need to make sure you're careful about the capitalization of the units. So let's compare molarity and molality in a little more detail. We see that we have our moles of solute in both. Those are the same. Okay. What we also see is that our liters of solution is different than the kilograms of solvent, and this makes a huge difference in the value. We have different symbols. One deals with solution, one deals with solvent. The big thing, and the reason we have to worry about using molality, is why not just always use molarity, is that molarity will vary with temperature. As I change temperature, I'm going to see a change in the volume, and therefore I will see a change in molarity. However, with molality, I know that the kilograms of solvent is going to be constant at any temperature. Okay? The mass of a substance is not going to change, and as a result, we can put kilograms of solvent, and then we can figure out what our molality is. So if I'm looking at something over a temperature range, which we'll do later in this chapter when we start talking about colligative properties, is we typically use molality there because we are looking at temperature changes. Now looking at mole fraction, we're just worried about the kind of part over the whole with respect to moles. So similar to a percent, but using moles, and we don't multiply by that 100. We use the symbol chi to represent mole fraction, and this is typically a unitless number. This is always a unitless number, one of the few that we see in chemistry. And so if I know the moles of solute, then I can solve for, and I can find the moles of solvent, then I can solve for the mole fraction. And we'll be using this from time to time, particularly when we start looking at some pressures and vapor pressure calculations. So let's look at an example here for mole fraction. What is the mole fraction of sodium chloride in a sample that contains 10 grams of NaCl in 75 grams of water? Well, the first thing I want to be able to do is identify what is my solute and what is my solvent. Okay. Now remember, our solute is a substance that's present in the lesser amount, NaCl. My solvent is therefore water, and it's the NaCl that I'm trying to find the mole fraction of. I could also find the mole fraction of water if I wanted, but that's not what's being asked for in this particular problem. So I'm going to look at the NaCl. So I need to get to moles first, and when I look at moles, what I'm going to find is that I have 10 grams of NaCl, and use my molar mass of NaCl, which is 58.5 grams per mole, and then I'm going to do the math there, 10 divided by 58.5, and I get 0.171 moles of NaCl. Now I'm going to do the same thing with my water. I have 75.0 grams of H2O, and I know I have 18.01 grams per mole for my molar mass. And I do the math, 75 divided by 18.01, and I get 4.16 moles of water. Now what I can do is find my mole fraction of NaCl by taking the moles of NaCl that I found here, and I get 0.171 moles, divided by the total moles here, so 4.16 plus the 0.171, because I'm looking at the moles of all my substances that are present. So I take 0.171 divided by, and I'm going to use my parentheses, so I make sure I do that addition term first, remembering our order of operations, and I add to that 0.171, and I end up with a mole fraction of 0.0395. No units with that because it is a mole fraction. And when I look at my moles that I started with, my moles of NaCl, my moles of water, I see that it's going to be a pretty small amount. I've got a lot of water and a very small amount of NaCl. Looking at our percent in parts per million and parts per billion, I can set these up in much the same way that we set up percents, and this should be something that's familiar to you, that because anytime I'm dealing with the percent, it's always part over the whole, and that's exactly what we're looking at here. And so the whole here is always going to be our solution. That means it has to include both the solvent and the solute, or the solutes if there are multiple solutes. And so it's part over the whole. This time we're looking at mass percent, which is typically what we do, and we look at the mass of the solute divided by the mass of the solution times 100. For parts per million, we take the mass of the solute times over the mass of the solution times 10 to the 6th now because it's parts per million, and then parts per billion mass of solute over solution times 10 to the 9th. Another way to write it is parts per million. If we're looking at by mass, then we can rewrite it as milligrams per kilogram. So if I had something that was 2.3 ppm, I could also write that as 2.3 milligrams per kilogram of solution, and my milligram is there as my solute. So it's just kind of a shorter way to get to the relationship between them if you're using this in a conversion factor. So when we started talking about molarity in 105, we talked about saying, well, instead of writing it the capital M, go ahead and write it as moles over liters, just to remind you what units are present. The same thing is true for parts per million and parts per billion. Instead of leaving it as the 2.3 ppm, go ahead and rewrite it to look something like this, and that way it's easier to see what units would cancel out. You do have to be careful because if I have milligrams of solute, I can't cancel that without, say, milligrams of solution. We have to have like units and like substances. For parts per billion, we see the similar thing here, only now instead of if I have parts per billion, so let's say I have 10.5 ppb, I can rewrite that as 10.5 micrograms per kilogram. And again, it's micrograms of solute and kilograms of solution. Don't forget to go back and look at those prefix definitions way back in the beginning of the book that we covered in 105, just to make sure you're familiar with those conversion factors. Now, we know how to calculate molarity and mass percent and molality, and that's great, but what happens when we're given molarity and we need molality, or vice versa, or we're given molarity and need mass percent? Well, we have to be able to convert between one set of units to the other. And the thing that we have to be most careful about is the units in our value. In particular, when we look at the denominator. If I'm looking here at molarity, I see liters of solution. If I'm looking at mass percent, I see my grams of solution. But when I look at molality, I have kilograms of solvent. So if I'm given liters of solution, not only do I have to convert that to a mass in grams or kilograms, but I also have to isolate the kilograms of the solvent. So we need to be careful about that. So when you're writing down units, go ahead and write them out. Moles over liters, moles over kilograms of solvent, so you're absolutely clear on exactly what you're trying to calculate. I'm going to stop the recording here and actually record a couple of separate videos looking at some of the conversions among these three, the molarity, molality, and mass percent, so that you can kind of keep those a little bit separated. If you have questions on any of this material, please feel free to post it on Piazza, and we'll also be doing problems in class on Wednesday. If you want me to work problems in class, you can also post that there. Have a great day, stay warm, and make sure you understand this content because it's going to be on the exam on Thursday.